Hey everyone, welcome back to the deep dive where we're all about getting you up to speed on the complex stuff. And today we're diving headfirst into some seriously cutting edge research.
Absolutely.
Buckle up.
Yep.
We're taking on a paper titled Convergence and Stability of Episodic Upside Down Reinforcement Learning, Goal Conditioned Supervised Learning in Online Decision Transformers.
Quite a mouthful.
It is a mouthful, but the concepts are even juicier. We always hear about AI dominating games, robots doing incredible things.
Mm-hmm.
A lot of that comes down to reinforcement learning, right?
Yeah, for sure.
But this one goes deep, like really deep into the theoretical nuts and bolts of some of the newest, most exciting algorithms in RL.
Yeah, it really gets to the heart of what makes these new approaches so powerful.
Okay, so let's set the stage here a little bit.
Sure.
Our listeners are smart, they're engaged, they probably follow AI and RL to some extent, but let's break down what makes this paper and the algorithms it analyzes so special.
Right. So you've probably seen the headlines about these algorithms, things like UDRL, GCSL, and ODT.
They're kind of rock stars in the RL world right now, right?
Exactly. They're achieving some truly remarkable results in really complex scenarios. But what's truly groundbreaking, what really sets them apart, is their core approach. They're fundamentally changing the game by inverting the traditional RL model.
Okay, inverting? That sounds intriguing.
It is. Instead of relying solely on that classic trial and error approach, these algorithms lean more heavily on supervised learning or sequence modeling techniques. It's a real paradigm shift, and this paper is one of the first to provide crucial theoretical insights into why this inverted approach is so effective and when it works best.
So instead of the AI kind of fumbling around getting rewards or punishments, it's more like they're learning by seeing the end goal and then figuring out the steps to get there, right?
You got it. Imagine a student learning math. Instead of just plugging in numbers and seeing if they get the right answer, they're studying worked out examples, understanding the logic and steps involved.
Ah, that makes sense. So it's like they're learning from a blueprint instead of just blindly experimenting.
Exactly. And this paper dives deep into three specific algorithms that exemplify this: episodic upside down reinforcement learning, UDRL, goal conditioned supervised learning, GCSL, and online decision transformers, ODT.
I'm already seeing how this is more sophisticated than just, rewarding a dog with a treat when it sits.
Oh, absolutely. This is next level stuff.
So these researchers, they weren't just impressed by the cool things these algorithms could do. They wanted to understand the fundamental why. What were the big theoretical questions they were wrestling with?
They were laser focused on two fundamental concepts: convergence and stability. First, convergence. Imagine these algorithms running in a perfect world, a simulation where they have unlimited data and computing power. The question becomes, do they actually settle down and find the absolute best way to achieve their goals? Do their strategies and values reach an optimal, unchanging state?
So if everything's perfect, can they achieve perfection? It's kind of like a theoretical limit, right?
Exactly. And then there's stability, which is all about what happens when you take the training wheels off when things get messy.
The real world, in other words.
Precisely. In the real world, things change unexpectedly, and our models are never perfect. So, how well do these algorithms hold up when the environment shifts a little or their internal model has some inaccuracies? Can they still find good solutions? Will their performance stay consistent despite these imperfections? That's what stability is all about, and it's super critical for any real world application.
So it's not just about being great in a perfectly controlled lab setting. It's about being robust in the wild, so to speak.
You nailed it.
Okay, so our mission in this deep dive isn't just to describe these algorithms. We want to explore the theoretical framework this paper puts forward to address these fundamental questions about their potential and their resilience.
Exactly. This paper is all about laying down some of the foundational math, providing the theoretical underpinnings to explain why these algorithms work so well.
I love it when we get into the theoretical nitty-gritty.
Me too, it's fascinating.
So let's get into it. What are some of the big theoretical innovations here? What did they bring to the table to grapple with these questions of convergence and stability?
One of the most significant innovations is that this paper really establishes a formal theoretical framework for this whole approach of using supervised learning or sequence modeling to crack RL problems. Before this, it was mostly about the impressive results, the empirical stuff.
Right, it worked, but no one was quite sure why.
Exactly. But this paper takes a huge step forward by framing the RL problem through the lens of supervised learning theory. It allows them to use existing analytical tools from that well-established field in a totally new way, giving us fresh insights into convergence.
So they're not just saying, hey, look, it works great. They're actually explaining why it works at a fundamental level.
Precisely. And to do this, they really dig deep into how the environment itself is mathematically described.
And how does that work?
Well, specifically, they focus on the transition kernel of the undenying Markov Decision Process, or MDT.
MDP, got it.
Think of the transition kernel as the rule book of an environment. It tells you the probabilities of landing in different states after taking a specific action. What's really insightful is how they analyze how the properties of this rule book directly influence the convergence and stability of UDRL, GCSL, and ODT.
Okay, so the environment structure, how predictable or random it is, that plays a huge role. What did they discover about that relation?
One of the central findings is that these algorithms tend to perform incredibly well, almost optimally, when the environment's rulebook, the transition kernel, is close to being deterministic.
Meaning,
Meaning, if the consequences of your actions are highly predictable, if things generally happen as you expect, these algorithms are much more likely to learn really effective strategies. Which makes intuitive sense, right? If things are super chaotic, it's really hard to learn reliable patterns.
yeah, absolutely. If you can't predict what's going to happen, it's tough to figure out what works consistently.
Exactly. The paper formalizes this intuition by proving, mathematically, that several key aspects of the learning process, things like the learned policies, their predicted value, and how well they achieve goals, are continuous when the environment is highly predictable.
Continuous meaning.
Meaning that they change smoothly and predictably as the environment changes slightly.
Got it.
And what's really powerful is that this holds both in the long run, after lots of learning, and even early on in the learning process.
So if the environment is consistent, the algorithm's learning is more likely to be stable right from the get-go.
Precisely. And even more impressive, they developed new mathematical techniques that provide the first concrete estimates for how quickly those learned strategies and values converge, and how stable they are when the environment isn't perfectly predictable. And these estimates are directly tied to how close the environment is to being deterministic. This is a huge step towards actually putting numbers on how well algorithms perform.
That is a huge leap, going from it to it works this well, this reliably. What kind of mathematical wizardry did they use to get to that level of analysis?
That's where the real theoretical magic comes in. They brought in some pretty sophisticated concepts that haven't been widely used in RL theory before. For instance, they talk about working in segment spaces.
Sounds complicated.
It is, but think of it like this. Instead of analyzing the entire, potentially infinite sequence of actions, they break it down into chunks, like episodes or short sequences of experiences. It allows them to zoom in on the learning dynamics within those individual segments.
Okay, I can see how that would make things more manageable.
Right. And then there's the concept of relative continuity using weak convergence of measures relative to compact sets. It's a nuanced way of looking at how different action sequences might lead to the same outcome and how learned strategies behave as the environment changes. It helps them handle situations where small changes in the environment might lead to seemingly large changes in behavior, but ultimately the final outcome is still pretty close.
So even if the exact path changes a bit, the destination is still roughly the same.
You got it.
Okay, with all these new tools, what were some of the more surprising or interesting things they discovered?
One of the really striking findings relates to EUDRL. The paper shows that the strategies learned by EUDRL can actually become discontinuous after just the first learning step.
Wait, discontinuous after a single step.
Yeah, especially in environments that are almost perfectly predictable, but not quite.
That seems counterintuitive. What does that mean in practice?
Suggests that the very first update in EUDRL is hugely important. It might be as influential as many later learning steps. It also highlights how tricky it can be to ensure that learning converges smoothly and reliably in environments that have even a little bit of randomness.
So that initial phase is crucial, and you can't just assume that running the algorithm for a long time will automatically make things better.
Exactly. The researchers really dug into providing a solid theoretical explanation for why EUDRL works so well in practice. They found that while it can converge to optimal strategies in perfectly predictable environments, it doesn't always guarantee a smooth step-by-step improvement or completely reliable convergence in more realistic stochastic settings.
It sounds like they were pretty honest about the limitations, not just focusing on the successes.
Definitely. They also looked at a regularized version of UDRL, which is a lot like online decision transformers, OBT. This involves adding a bit of randomness to the algorithm's choices to make it more adaptable. Their analysis of this regularized approach was pretty general, not limited to specific types of environments.
And that regularization idea is something that's used a lot to make learning more stable, right? It encourages exploration.
Exactly. It helps the algorithm avoid getting stuck in suboptimal solutions. This paper helps us understand why regularization works so well within this new paradigm of RL. It's important to remember that their analysis focused on simplified scenarios, finite, discrete environments, without the added complexity of things like neural networks, which are essential for real-world applications.
So they're building a solid foundation, making sure we understand the basics before tackling the messy reality of truly complex environments.
Exactly, laying down the fundamental principles first.
This has been a fascinating journey into the theoretical heart of RL. Let's recap. What are the key theoretical contributions of this paper? What are the big takeaways?
Well, this paper delivers a crucial foundation for understanding RL algorithms that use supervised layering or sequence modeling. They rigorously analyze how well these algorithms find the best solutions and how stable they are, emphasizing the importance of the environment's dynamics. One of the key insights is the strong link between near optimal performance and predictable environments.
Got it.
And they didn't just observe that connection, they developed the mathematical tools to estimate how quickly and reliably learning happens in relation to the environment's properties.
And those estimates are huge, right?
Oh, yeah. They also introduced entirely new concepts to RL theory, things like working in those segment spaces, using sophisticated topology to analyze continuity, and even bringing in fixed point theory from dynamical systems.
Mentioned their deep dive into EUDRL. What were the key insights there?
They aimed to provide a theoretical basis for why EUDRL works so well empirically. They found that its strategies can become discontinuous very early on in certain environments, highlighting the critical role of the initial learning phase. They also extended their analysis to a regularized version of EUDRL, which is similar to ODT, using the idea of entropy regularization.
And all of this was possible thanks to the use of advanced mathematical frameworks, especially topology.
Exactly. Their use of a topological approach, incorporating ideas like relative continuity, really expands the mathematical tools we have for understanding RL at a deep level.
So to wrap things up, what's the big picture for our listeners? Where is all this theoretical work leading?
The most exciting thing is to think about how these new theoretical tools and this focus on the environment's properties could completely change how we design and understand RL algorithms in the future.
What are the implications for real-world applications?
Well, as we try to deploy these powerful algorithms in messy, unpredictable real-world scenarios, having a strong theoretical foundation like this becomes even more crucial. So, what groundbreaking advancements in RL might emerge from these deep theoretical insights? That's the big question this research leaves us with.
Food for thought. And it's delicious food for thought. Thanks so much for illuminating this fascinating research for us today. For those of you who want to dive deeper into the paper itself, we'll include a link in the show notes. And join us next time for another insightful exploration here on the Deep Dive.